Hello everyone, this is Professor Jeff Wilkerson at Luther College. What we're going to do this week is we're going to get prepped for lab, for general physics. We're going to be measuring using Ohm's law to measure resistances. And we will explore regions to see if all of our devices are ohmic. We'll continue this in the coming weeks and we'll look at resistors to see, by now this should be fairly familiar to you, what we do, those of you who are in this course. We'll look at this board. This board's got resistors that are marked 10 ohm, 51 ohm, 51 ohm, 68 ohm, 68 ohm. So this week we're going to be looking at these 6 smallest resistors. There are 3 bigger resistors that we'll use in a timing circuit with that capacitor in coming weeks. But what we're going to do this week is we're going to explore there and do what we do. We're going to use Ohm's law to measure the resistance of each of those resistors and to determine various confidence intervals for what that resistance might be. So we're going to make the measurements over and over and over again, a lot of different resistance measurements, and say, okay, how confident are we that the actual value is, does our, let's say it that way, is our data that we take consistent with these actually being exactly 10 ohms, 10 ohms, 10 ohms? Is 10 ohms within our say 95% confidence interval or something along those lines? Or we'll take the difference between what we measure in 10 ohms and ask how likely is 0 to be in that range. So we've done this quite a bit by now. Hopefully we're getting good at it. And hopefully you know Ohm's law and you're ready to apply Ohm's law. So what we're going to do is we're going to use this external power supply right here. And let's just start. We're going to bring some power into the board. So we plug the red into the red knob, the red outlet, and into the board right there. And then we're going to come from the other side and bring the negative back into the power supply here. Now we have to complete a circuit. So we need this current to go someplace. So we're going to bring this in from this direction, and we can trace the board. You can look on the back if you can't see it through the board. The black is connected directly to that 35 pole right there, and so that's our negative power. Our negative voltage comes in right there. The positive of our potential is connected over here to this pole right here, and so we're gonna power into there. So first thing we're gonna do is let's just look at one of these resistors right there. Suppose we want to look at the 10 ohm resistor. We need to get the power, the positive pole. So we need to create a potential difference across this resistor. So remember, we measure potential across, current through, potential across and current through. So we want to get a potential difference across this resistor by pushing a current through there. Or another way to say that is to say get a current through there by creating a potential difference across it. That might be a little bit more accurate. So we're just going to take one of these wires with the alligator clips on it, and we're going to clip from the positive over here to this positive. By doing that, this 10 ohm resistor has now a potential that's the positive potential on this side. If we bring another wire with alligator clips on it, and we clip from the other side of the resistor back over to the negative of the power supply, down in here, you see what we just did. So this side of the resistor is being held at the negative potential of the power supply. This side of the resistor is being held at the positive potential of the power supply. We're going to drive a current through there. Okay? We're going to create a potential difference across here and drive a current through that resistor. So let's do it. Let's see what we want to do for this first week. I'm going to turn the power on here. I'm going to make sure these knobs are down when I turn the power on, the 2 left ones. Those are the voltage knobs. Those are the potential. We'll turn the potential up with those, coarse and fine. I'm going to have this knob turned all the way up to the right. That's the current limiter. So it'll allow this device to drive as much current as it possibly can. Power's on. We're not going to trust the readings here. We're going to measure the current with this and the potential with this, or you could do it vice versa. You could try it both ways. I encourage you always to try your equipment try to measure the current with this device and the potential with this device and see what you get, see what you trust. So in any event, I'm going to start. I want to measure the potential across here, and if I want to measure the potential across here, I'm going to clip in this. I'm going to put this into the ground outlet. So this is the common right there. And I'm going to put this probe into the one that's marked voltage up here. So we've got the voltage right here. I'm going to turn the power on to this device. Yep, there it is. And I've got this turned right now to the 2-volt scale, but you can turn that to a millivolts, 200 millivolts, 20 volts, 200 volts as needed if you peg this thing out. So I'm going to put the red one on the high side, on the high potential side of the resistor. I'm going to clip it in over here. I can clip it right to the pole. I can clip it to the lead of the resistor. Try it both ways. See if it makes any difference. Probably shouldn't, but give it a try and see. I'm going to click the low potential, the negative one, over to this side, and then I'm going to start to turn up the voltage here with the fine knob. So watch what happens to these numbers as I turn up the fine control knob. We're starting to get a little bit of potential difference across there. We're starting to drive a little current through there. And I'm reading the potential difference over here. It says 30 millivolts, 0.030. I could turn this to the lower setting and get another digit, 29.9 millivolts. That's great. I keep turning this up, keep turning this up, keep turning this up. First thing I want you to do, each resistor, I want you to take, this is a 10 ohm resistor. You know that the power that's being deposited to that resistor, energy per time being dumped into that resistor, is V squared over R, the potential difference across the resistor squared divided by the resistance, or I squared, the current going through the resistor, times R. Both of these things are true. They can show they're consistent with one another by using Ohm's law. And I want you to calculate what potential difference across there and what current through there you can have if you want to keep the power being delivered to that resistor below, say, 1/4 watt. Let's say 0.25 watts, and say we don't want to go above there. If you go above there briefly, that's okay. And even at that top power, maybe we don't want to leave it there for a long time. So we don't want to be driving a lot of power, dumping a lot of power into this resistor for a long period of time. So let's figure out what 1/4 watt is, and maybe we go up to 1/2 watt, but we don't want to spend a lot of time up in that power range. So let's try to keep our power deposited relatively low in the resistor so we make sure we don't burn it up. So we can measure this, and we're going to just measure, we're going to use Ohm's law and measure this potential across the resistor and current through the resistor. But we're not measuring the current through the resistor, you see right now. We get a current reading right here, but we don't trust the current reading here too much. So we're going to power this back down. And we're going to say where this comes out of the negative side, where it comes out of the board and back in, we're actually going to take this over to this meter and use this meter. See, we're across. We measure the potential across by clipping across our resistor. We're going to measure the current through by bringing this in. Now, this is the high side, so this has to go in, say, here to the milliamp microamp setting, because that's the current setting, and the low side has to go through to the common, to the ground setting right there. Now you'll look at this and you'll see it says, oh goodness, it's fused at 400 milliamps max. So we're not going to let this get over 300 or 350 milliamps. If it does, once you get to 350 milliamps, turn it over, shut everything down, move this over to this setting, and that says that's fused at I don't see where it says 10 amps max. Okay, so you don't want to get that above 10 amps. So you get up there. So okay, so let's start again now that we've done this. Let's turn this on, and let's start dialing our voltage up again, and we can measure. Look at that. We can measure 20.4 millivolts. Record that and kaleidograph it in your lab book, and it looks like 2.044342. So that's interesting to see how much it jumps around. 4.5. Is it walking one direction? Is it changing? What does that mean if it's walking one direction? So you're going to say 2.05 milliamps is a good call right there. So you look at that and you say that's how many milliamps the current you have there. 2.045. You see jumping around. You make a decision what that is. Then we're going to tweak it up just a little bit more. Not much. 29.3 millivolts. 2.93 something milliamps, and up, and up. And you can make a whole bunch of measurements. Just get a whole bunch of measurements down in this range, And as this approaches, it says 40 milliamps, you see. As this approaches that 40 milliamps, remember we were fused at 400 milliamps. We don't want to get above 350. So as we're turning the fine control knob right now. The coarse control knob's all the way down. As we get this up here, as it approaches 40, it's not going to get there with the fine control knob. Okay, we got to 35. So I'm going to turn the fine control knob all the way back down. And I'm going to start up with the coarse control knob. It's going to go much faster, so we're going to be much slower and more careful here. There we go. Overload. Took a second. Bam. Now it went up to the 400 milliamp scale. So now we can measure up to the 400 milliamps. And as I keep going, I've pegged this out. I've got to turn this up to the next setting. I've got it. Okay, good. It says it's 0.835 volts. And it's 84 milliamps up there. So we're going to record that as best we can. And this all looks good to me. So this looks like what we want to do. We've got our measurements. We want to hook things up in different ways and see if we get measurements that are consistent. Try ramping up the voltage. Don't go above too much power dropped into your resistor, and then ramp the voltage back down and ramp it up and ramp it back down and get a whole bunch of measurements of the resistance. Look in different regions where you're up near the maximum power that you're delivering to this resistor and down to very low power being delivered to this resistor, and scan the whole way. Because one of the things we're going to look for is this device ohmic? Is the resistance, does it appear to be unchanged with time or with potential difference or current? So to say, if we drive a lot of current through there, does the resistance look like it's changing? Or if we drive very, 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 very little current through there, is the resistance different from what it is at other times? So we're going to have a lot of data on either end and blow up graphs and look for differences between the resistance at the low end or the high end and the mean resistance, and we'll apply all the statistical tools we've been practicing and developing to decide, does this device look like it's ohmic or not? And we're going to do this for each of these resistors. We want to measure the 10 ohm, 10 ohm, 51 ohm, 51 ohm, 68, 68. And we're going to ask the question, do they all look ohmic? Do they all look good? Do they all look like the 68 is right? And is this 68 the same as that 68? Is this 51 the same as that 51? Is this 10 the same? Or can we measure a difference? We take the one minus the other. We've done this a lot. And measure that difference and say how many standard deviations of the mean is that difference away from zero? And ask, how consistent likely are they to be the same resistance values? And we're going to understand all these. You're going to draw a sketch in your lab book to make sure you remember which resistor is which, and they're numbered on there, R1, R2, R3, R4, R5, R6. Your board is lettered H, so you're going to record that in your lab book to make sure you have the same board and the same resistors and all of this stuff, and you understand what's going on. And we're going to, this week, really understand these resistors. As we have time, I want you to start hooking these up in series. Think about how you have to do it. Sketch it in your logbook and think about how you need to measure the resistance, how you need to hook these up so you can measure the resistance of 2 in parallel, or 2 in series, or 3 in parallel, or 3 in series, or different combinations of parallel and series. And so we're going to explore that this week and into next week. And as we get into the next week, we'll also do a little bit of timing, a little bit of RC timing over here with these resistors and this capacitor. So we'll shoot a video for that too to give you an introduction how to do that. But hopefully this shows you how to set the board up and you can follow this through and think about what you're doing. Think about not driving too much current through these resistors. Think about how you're going to use Ohm's law to determine the resistance of each resistor and to figure out how stable it is. Maybe you go up, maybe you turn the voltage up one time and you get a certain resistance value, you turn it back down, you turn it up the next time, you get a different resistance value because maybe you're heating this thing up or something. Maybe it's changing just a little bit with time. That would be an interesting thing to know. So you want to know how stable the resistance is and how close it is to that 10 ohms that's marked right there. And is it the same in different regions of potential difference across there, different regions of current passing through there. That's pretty much what we got. That's our introduction to the first week of our DC Circuits lab, where what we really are doing is using Ohm's law to measure resistances of devices that are called resistors. So somebody's worked pretty hard to engineer these devices so that their resistance is what they claim it is, and it is stable. And so we want to see how good a job they did. In a couple of weeks, we're going to look at these light bulbs over here and ask, are those ohmic? Or does the resistance of those change? Those are devices that have not been engineered. for the resistance to be stable, and we'll see if we can see the difference between these light bulbs and these resistors. So that's what we got. We'll see you in lab this week, everyone. Have a good week until then.